Alright, if we continue from the previous video, the last thing that I did with you is determining oxidation numbers. So here's a little exercise, and this exercise looks at if I had these compounds in front of me, or ions, anions and cations, how would I determine the oxidation numbers? Alright, so when you're done, so what you're going to do is you're going to show the method. Alright, you're going to show the method to finding the oxidation numbers of the following compounds, ions, and molecules, and show all working out. You need to practice, because what comes next gets very, very complicated. So you need to get this part of it sorted out in practice. Just like how you did naming compounds in grade 10, it's very important that you do this section or these types of examples thoroughly. So when you see it, and these are the common ones, when you've seen it, you really know what's going to come. Alright, so please make sure that you get through this exercise. When you're done, you can send me a message and I will send you the memo. Alright, over here we're looking at the introduction to redox reactions, or like we say, we can call them oxidation reduction reactions. Right? In oxidation reduction reactions, there must be a movement, or rather a transfer of electrons. Right? So there is this movement that's going to take place between atoms. Important. So if I had atom A over here and I had atom B over there, atom A is going to transfer and give to atom B an electron. So if there is an atom that will give and an atom that will receive, right, then I'm in a situation where I have a redox reaction. So I know from previous videos that reduction is a gain in electrons. And when we spoke about it, we spoke that if something gains and it becomes reduced, it sounds a little bit weird, but we're going to get into that now. Oxidation is a loss of electrons. And so just remember that when we talk about gaining and losing, if this one over here, or this one, let's say this one over here, it loses 2 electrons, right? Let's say it loses 2 little electrons, then those 2 electrons must be gained here. If it lost 7 electrons, and so on and so on, it must make sense. So in this situation that I have here, atom A is losing an electron. So I can say that oxidation is taking place at atom A. And atom B is gaining an electron. So the process that's happening there is reduction. Right? Now, when we talk about losing and gaining, we have to use the right terminology. So if I was looking at atom A here and atom B here, and I know that here I have reduction, and there's a transfer over there, and here I have, oops, sorry, I don't have reduction. Over here I have oxidation, and over here I have reduction. Then we can write a statement. We can say that A is being, and we must use the right word, oxidized, and B is being reduced. So if B went and gained an electron, what do we mean by it's being reduced if it's gaining something? And that's the confusing thing, because it doesn't quite fit in. So why does a reduction mean gain? And usually when we say reduced, we mean that it gets less. So I want you to think about it like this. Oops. Electrons are negatively charged. right? Let's put this here. They're negatively charged. And if I had to, let's say I had 3 plus, 2 plus, 1 plus, 0, 1 minus, 2 minus, 3 minus. The only way I'm going to go from here to here is I need to add in electrons. And if I add in electrons, then the charge gets smaller. It's being reduced. So by adding electrons, so I can say as electrons are added, the charge, that's important, reduces. And they're going to ask you in an exam situation, why is it weird, or why is there how can you gain something and reduce? You need to be able to explain it. And this statement over here is a good statement of what we mean by reduction. Now there's two ways of us remembering it. The first one we call it oil rig, right? If I to split it up, it means oxidation oops, let's put it better. I can say oxidation is loss, oil, which means reduction is gain. Right? That's one of the ways that you can remember that. Or you can do Leo the lion says grr, and you have loss of electrons is oxidation, and you have gain of electrons is reduction. So there are two ways of us. You can either use the oil rig, or you can say Leo the lion goes grr. And those are two ways of us knowing or remembering these things, because if you confuse the two, you're going to do all your calculations is incorrect. Everything's going to be a mess. So you need to find one of these two things that resonates with you so that you can use it to memorize. All right, so oxidation and reduction happens in all sorts of reactions. They're very important. You'll see how common they are in types of reactions you've already worked with. So in the next little part that we're going to be doing, we're going to be looking at examples of how do I decide, is this a redox reaction? Is this not a redox reaction? So those are the types of things that I need to be able to identify. And the only way that we can do that is by using oxidation numbers. So not only should you have your oxidation numbers in front of you when we're going through the next examples, but you also need to have that exercise that you did where you learned how to find oxidation numbers. All of that becomes very, very important in the next section. Alright, in this next one, we're going to be looking at a bunch of examples. Let's look at the first one, right? The first one says sodium and chlorine combine to make sodium chloride. Right? So when I write this out, I can say Na plus Cl becomes NaCl. Right. So let's just break this down before we even begin this whole situation. Right. The first thing I have to look at is, and you can see I haven't balanced or anything, I'm just looking at this. When I start here, all right, I need to look at the charges. So the first thing we do is we look at the charges. If I look at Na and Cl, right, when they are reactants, they are both electrically neutral atoms. Right? The electrically neutral atoms. And when they're on their own, so when they're on their own, they have no charge. Great, right? So what happens then? On the other side, if I'm looking here at the NaCl, here, how does it become NaCl? Right? In order for me, I can see here that I have an ionic bond because I have got sodium, which is a metal, and I've got chlorine, which is a non-metal. Because it's ionic, that means that something had to have a cation plus an anion. Now, the only way for something to become a cation or anion, you need something that's positively charged and something that's negatively charged. So if I'm starting off here at the beginning with neutral and neutral, how did that become that? So the second thing that happens is that the sodium, when they come into contact with each other, the sodium is going to give the chlorine one of its electrons. And we know this because this is one of the most common examples that we use. So you're basically going from Na, which is positive, which is neutral, to Cl. So all I'm seeing is that transfer, that electron moved across. So here I can say that sodium lost an electron, and chlorine gained an electron. And if sodium is going to lose an electron, it's going to become more positive. So I'm going to be left with Na with a charge of 1 plus. And chlorine gained, so it becomes Cl. It was at 0, and now it's Cl, 1 minus. And because these opposites attract, and I know that, because I need a cation and I need an anion to make an ionic compound, they're going to stick together. So what I'm going to end up with is I have this plain Na here, Na plus, and I have a Cl minus here. And because they're going to be attracted to each other, I'm going to be stuck with NaCl as a full compound. So I end up now with sodium chloride. Chloride. All right. So I start off with, let's put it like this. Oops. I start off with something that's electrically neutral. All right. There must be an electron transfer. These are the steps. There must be an electron transfer. When I have an electron transfer, I must have ions with opposite charges. Right? And once I've got that, there will be an attraction between ions. To bond. Alright, so I've got that sort of set up. So let's have a look here at how this kind of works out for us in terms of oxidation. Alright, so if I'm looking here, I've got Na plus Cl, and I'm going to get from that NaCl. Right, so when I look here at oxidation numbers, I notice here that there are no charges because they're atoms standing by themselves. So I know that according to my rules, if I have an atom, I need to see that the oxidation numbers are 0. So over here I have an oxidation number of 0, and over here I have an oxidation number of 0. Alright. Now when I get to this side, how this actually formed was there was electron transfer. So when I'm looking at sodium charge is actually +1. And chlorine's actual charge is -1. And together, they have no charge. Oops. Because at this point, they are completely neutral. Because I know from my rules that all compounds or molecules should have no charge. So let's try and explain this in terms of oxidation and reduction. Because if I'm looking here, my Na started off at 0. It lost electrons and became +1. My chlorine started off at 0 and gained electrons. Right? So here there was a loss and here there was a gain. So in terms of oxidation and reduction, I can say that Na, and what Na actually did was it lost an electron. So Na losing an electron was then oxidized, and chlorine, which gained an electron, by gaining an electron, is reduced. Right. So I've got here pictures, words, equations. Let's have a look at how we break this down. So what we can say is that in terms of the chlorine, I'm just going to do them next to each other. I can say that Cl is reduced. So what actually happens here is I need to show this in something we call a half reaction equation. A half reaction equation. Right. So I have chlorine, and when it was reduced, it was gaining. So chlorine plus an electron gave us Cl1-. So chlorine gained an electron. So that's how you write down a half reaction. And what we call this is the reduction. Half reaction equation. Now when we write a reduction equation, the electron must come together. It must come together with the atom. That's very important. It must come together. As in, when I look at the formula, can you see here? The atom and the electron are coming together. They're on the same side in that way. Right? If I look at the other one, right? The other one, I'll do another color, is sodium. And I know of sodium that the Na is oxidized. Alright, so this one's a little bit complicated because what's happening when it oxidized, it lost. So when that happens, we have to actually look at this. The Na, right, minus an electron and became Na plus. But our problem comes through with this situation. You are not allowed to have a minus sign. So this whole thing would be considered incorrect in terms of writing it out, because there's no such thing as a minus sign. The sign that must be there must be a positive sign. So how do we sort this out? How do I show this type of question? All right. So what we need to understand is that in oxidation, right, an electron must leave. So if I have Na, how do I get Na? I have to have Na. So how do I get this to be neutral? I need to have an ion, Na plus, and added to that ion, I need to have an electron. So this type of reaction is an oxidation reaction. And in an oxidation reaction, the electron is what we say it's spit out. So I must see an electron at the end. So can you see in this one where the electron is, the first one? There's the electron there. This one, the electron must be an N if I'm writing an oxidation reaction. So I can say that an electron on the left of a balanced equation means it is coming in, because it's on the side of the reactants. All right, and an electron on the right of a balanced equation means it is leaving. So you're always going to see it on the product side. Now that's important to us, because when I see that happening, so let me just sort this out. When I see that sort of situation happening, I should know that over here I've got reduction, and over here I've got oxidation. All right. So when we're doing this sort of section, this is very, very, very important. You have to know how to write half reactions. You have to know, if this is the situation that's happening in front of me, how do I write the half reaction for oxidation? How do I write the half reaction for reduction? I'm going to work through a few of them with you. It is a little bit nitty-gritty. So let's go over here to the next part of this whole thing. Right, so we know now that in my formula, I've got 0 and 0 there. This is plus 1. This is negative 1. So when I connect it like this, I know that I've got the oxidation of sodium, and I've got the reduction of chlorine. Have a look at where I'm writing these oxidation numbers. I make sure that I write these oxidation numbers at the top. So I actually have, what's happening here is I have two processes. All right, the first and like I said, we call that the half reactions. All right, the first process I have is the oxidation reaction. And if I have an oxidation reaction, it's Na gives me Na plus an electron. And my second process is the reduction reaction, and that gives me Cl plus, an electron gives me Cl minus, right? These two reactions that are happening must be at the same time. It must be at the same time. So as you can see that the electron that sodium gives up is the same electron that chlorine gains. So we understand that oxidation and reduction must happen at the same time. These are only half reactions, right? They don't, if we look at something like this or a situation like this, they only tell half the story, each half equation. They don't give the full equation. When we put it together, they're going to give us a full type of equation. Right? So don't forget, oxidation and reduction must exist together. If an atom in a compound gives up an electron, something needs to take up that electron, and if I have that situation, I have an oxidation and reduction type of equation. And let's have a look at a second example. Let's look at this example. It says, does the following example represent an oxidation reduction reaction? So I've got a K plus ion, potassium ion, plus a chlorine ion, and then I get something that's neutral. So is it redox? No, it is not, right? Why you would think it's redox, or why you might have said yes, it's redox, or thought yes, is because if you see a plus, or rather a positive charge, and you see a negative charge, you might think to yourself, I have ions. And if I have ions and they plus and they minus each other, I'm going to have redox. That is not the case, right? What you need to understand is just because I see charges does not mean it's a redox reaction. Therefore, if we think of oxidation reduction reactions, we must understand that there must be a transfer of electrons. Right? There must be a transfer of electrons. So if I looked at this situation, I've got K plus Cl minus gives me KCl. Now, if I'm looking here, I've got plus 1, I've got minus 1. But in order to form this thing over here, this potassium must also be plus 1, and this must be minus 1. So when I connect them, look here, it starts off as plus 1, and it ends up at plus 1. This starts off at negative 1, and it ends up at negative 1. So in that situation, I can see now that I don't have a transfer of electrons. So for this reaction to be an oxidation reduction reaction, the K plus and the Cl minus will have to transfer. But these atoms already have charges, because what I'm going to get here is I'm supposed to have K plus Cl minus. That's the only way that I'm going to get that sort of situation. I must have that transfer. But when I look here at the beginning, I have ions already. They already have those charges. So when I'm looking at the two, it starts off at plus 1, ends up at plus 1. If I see that situation, I know that I have a situation that is not a redox reaction. All right, so let's see what this means. If I have something that is not redox, then it must start off in a situation like this. It must have plus 1, minus 1, plus 1, minus 1. Then I can say here that it is not redox because there is no transfer of electrons, right? If I were to make this a redox reaction, you need to have a look at what happens. With redox reactions, if I have K, potassium, plus chlorine, and I end up with KCl, I've got no charge there, no charge there. Because this is an ionic compound, I'm going to have plus 1 there, I'm going to have minus 1 there. So I can see here that my potassium goes from 0 to +1 because there was a loss of electrons. And my chlorine goes from 0 to -1, which means it gained electrons. Oops. So in this situation, K is oxidized, right? And I can see that because the K transferred its electron to the Cl, right? And chlorine is reduced, right? So when I go from neutral to charges, then I have an oxidation reduction reaction, right? I have redox. There must be that transfer. And if I have a look here, if I have K plus and I have Cl minus, I can see here that there is no transfer. So when you're doing these types of calculations, you have to take into consideration what is going on in terms of how are my charges, am I gaining, am I losing, and if nothing's happening, then it's not redox. And you're going to get something like this in a test and exam. Just as a trick question, you need to make sure that you are prepared. All right, the next thing we're looking at is something we call oxidizing agents and reducing agents. When we look at oxidizing and reducing agents, we want to know what are they, what do they do, how do we identify them, and what do we mean by chemical agents. So I know, and remember I said I'm going to write this over and over again so it's branded in your brain at some point. Oxidation I know is loss of electrons, reduction I know is gain of electrons. I also remember this diagram that we drew earlier on, is that this atom transfers this electron, so one atom must lose, the other one must gain. And remember what I said, it could be many, 1, 2, 5, whatever the number is, we must, whatever it's giving up, something must receive it, and then we can say that if it loses, it becomes oxidized, if it gains, it becomes reduced. Now this new word comes through here is the word agent. Now when I want you to think of agents, I want you to think about movie stars and celebrities, and you've seen it in movies and so on, that if I have an agent is someone who makes things happen. So they book your interviews, they get you a new gig, they advertise for you, they get you endorsements and so on. So when we talk about an agent is something that makes things happen. That's what agents do. And so what we can say is that an oxidizing agent makes oxidation happen, and a reducing agent makes reduction happen. Alright, so let's talk about the things that something would have to do in order to make oxidation happen or make reduction happen. Alright, we're going to have a look at oxidation first, right? So if I'm looking at oxidation, and what does something have to do for us to make oxidation? So from our diagram we can see this is this initial setup. I have A over here, and A is being oxidized. It's losing those electrons. But it's really important to remember that atoms cannot just leave, right? There must be something that must receive. So I know that an atom, just make sure you're writing down all of this information, can only get rid of an electron if there is something else that is going to take those electrons away. Right? So in other words, when it's doing this, it must give it away to something else. Oops. So in this situation here, what's happening here is that A gives electrons to B, right? And remember, if something is going to gain electrons, it's going to be reduced. So A gives electrons to B, and what the result is of that is that it reduces it, right? So at the exact same time, let me just put some bullet points here so it can work. B takes electrons from A, right? And if it takes the electrons away, it ends up oxidizing it. So let's reduce this. To make oxidation happen, something must take electrons. So look here, to make oxidation happen, something must take electrons away from the thing that is being oxidized. So what's causing this whole oxidation process is that you have here in our diagram here A. Here's another color. I've got A over here, and A is trying to get rid of these electrons. And we've got B over here, and B takes those electrons. So I know that B takes electrons from A, oxidizing it. If this situation happens just like this, then I have oxidation taking place. So B is the thing that's saying to the A, give me your electrons. And if I have that sort of setup, right, then I can say that B is the oxidizing agent, right? The reason being, number one, it helps A to lose electrons. All right. Or we can say it also takes electrons from A. So when I look at my definition of an oxidizing agent, I'm looking at something that's going to take electrons. So I can say that B is the oxidizing reagent. And if it's the oxidizing reagent or oxidizing agent, because it causes oxidation. So yes, I can see that B over here is being reduced. And how it becomes reduced, it gains electrons. And by gaining those electrons, it's causing an oxidation process to take place. So it becomes then the oxidizing agent. So it's a little bit opposite. It takes a little bit of time to grasp all of this, but we'll get the hang of it as we go on. So that's how we sort out oxidation. It's how we look at how do I get an oxidation agent, oxidizing agent? How do I get a reducing agent? Now let's have a look at the next one, which is reduction. And now let's look at reduction. With the reduction, I've got my same setup. I know that A loses electrons, B gains electrons, which means A is oxidized and B is reduced. And in our diagram, we have this B that's gaining some electrons. But remember, oops, I'll just move a bit down. You cannot gain, or rather we can say create, matter. And because of that, it means you can't just gain electrons from nowhere. In order to gain electrons, something must give up in order to take it on. Right? So something must give it up. Alright, so to make reduction happen, something has to give electrons. Right, to the thing that is being reduced, which I know is B, right? So to make reduction happen, something must give electrons. And the other one, to make oxidation happen, something must take electrons. So where are these electrons coming from that B has to gain? It's coming from A. So what's happening now is that A gives electrons to B, right? Reducing it. That means it must have a less charge. Remember what we said? We're adding electrons. And since A is making this whole thing happen, so A creates this situation of reduction. All right? We can say that A is the reducing agent. All right? So if I'm looking here, I can say that B takes electrons from A, reducing it. As a result, A is the reducing agent. So if I'm looking at what's happening here is that whatever creates the opportunity, we've got to give that the name of the agent. So if I'm it's basically a switch that's happening. So the thing, let's do another color, right? So if we look at this little summary over here, so let's just go here. I'm just gonna split it up here. Sorry. Oh wait. Okay, just have a look here. Sorry. So what we can say, the thing is that is oxidized, the things that loses electrons will become the reducing agent, and the thing that's reduced, which gains electrons, will become the oxidizing agent. Or we can say that the oxidizing agent makes oxidation happen by gaining electrons, and the reducing agent makes reduction happen by losing electrons. So these are the four different ways that you can use. Let's number it rather. 2, 3, and 4. Right, they're the four different ways or things that you can use to explain what do you mean by oxidation reaction or oxidation agent and reducing agent. So there are two different summary points or ideas that you can use when you're doing tests or exams or exercises and so on. When you're done with this, you're going to go to the next video. It's going to be redox reactions 4. In redox reactions 4, we're going to be looking at oxidation and reduction examples.